Hi everyone, my name is Shobha Devakar. I'm an engineering director at Google. I manage the YouTube ads machine learning team, and my team is responsible for building all the machine learning models used for making ad recommendations on YouTube. Next slide. YouTube is video for everyone. Viewers have diverse content on YouTube, whether it is staying updated with the latest news, keeping fit with at home workouts, or entertainment content. Viewers can find and discover content and creators that reflect their diverse experiences and passions. Next slide. YouTube has many surfaces for content. The home page is what you see when you first open YouTube. It displays a mixture of personalized recommendations, subscriptions, and the latest news and information. The watch page appears when you're watching a video. It suggests additional content based on whether you're currently watching alongside other videos that you may be interested in. The search page delivers relevant search results based on the viewer's query. Next slide. YouTube ads are the ads which show up on all surfaces on YouTube. There are text, image, and video ads which are interspersed with the organic content on YouTube. Next slide. Next, I'll talk about different goals of the YouTube ads recommendation system. We build models and make recommendations across all surfaces, formats, products, and aim to deliver viewer satisfaction, advertiser value, and support the creator ecosystem. Next slide. Deciding which ad to show in all these places requires us to predict which ad should be shown in the current context. We build many machine learning models across surfaces, formats, and objectives. All these models are used for scoring and recommending which ad to show. Next slide. We want to make sure we pick and show good quality creatives to users to create a pleasing, engaging, and safe ad experience. An ads ecosystem needs robust, scalable mechanisms to safeguard users from bad quality ads. Ads are considered bad quality if they are racy, offensive, clickbaity, or overall bad quality. Next slide. Ad creators typically contain different combinations of modalities like text, images, and video, and any system that flags bad quality ad content needs a holistic multimodal representation of the ad. We build a multimodal model which combines all these modalities and makes predictions about ad quality. This is then used to filter ads on YouTube. Next slide. Next, Bharat is going to talk about how the model is built.
Thank you, Shobha. I will talk about the details of our dataset collection methodology and model architectures next. Our process for collecting a labeled dataset of ads and their quality is as follows. Trained human evaluators are given ad datasets and a criteria of bad quality. They evaluate the ad and assign a quality score ranging from 0 for highest quality to 100 for the lowest quality. We impute over these provided scores, which is typically an average, and then designate that to be the final quality score for the video. We collect a labeled dataset of about 600,000 ads for this study and reserve 20% of that for evaluation and the rest for training. Next slide, please. Coming to our input features, we focus mainly on two modalities, text and video. For the text modality, we concatenate the title and description of the video and run that text through a pre-trained BERT model. For a very quick primer on BERT, these models tokenize the text and produce dense float embeddings for each token through a stack of self-attention layers. In our case, the outputs are 1024 dimensional and we consider up to 512 tokens per ad. Next slide. Coming to the video modality, we use a pre-trained computer vision model that is a variant of ResNet to encode each video frame. Specifically, we consider the penultimate hidden layer output and average over pixels to obtain a 64-dimensional representation. We sample 1 frame per second, considering up to 60 frames for each video and zero pad as necessary. We borrow from previous work to add a sinusoidal positional encoding for each frame in addition to the ResNet embedding. A thing to note is that our unimodal encoders are fixed and we focus mainly on the multimodality in this work, and we'll go into the details next. Next slide. Now coming to our overall model architecture, our goal is to predict the quality score for an ad given the unimodal representations we discussed. There are two subnetworks here. First, a multimodal encoder, which consumes these unimodal representations and outputs a joint multimodal embedding. And then a tasked subnetwork, which is a simple feedforward layer that predicts the quality score given the multimodal embedding. We focus most of our experiments on the multimodal encoder in this work. Next slide, please. So we are chiefly interested in evaluating transformer models for learning a multimodal embedding. Given our two input sequences, ftext and fvideo, a lot of different architectural choices exist. So the figure on the right tries to capture the different possibilities with various flavors of attention modules such as self-attention and cross-attention. Different instantiations of this architecture lead to information fusion at different levels of the stack, and we discuss them in detail next. The first technique is early fusion, where we simply concatenate the two input sequences to form a single sequence and operate a single transformer with self-attention layers on this. The expectation here is that the model automatically discovers relationships that span across modalities. Next slide, please. On the opposite end of the spectrum is late fusion, where we fuse information only at the very end. We let independent transformer models operate on each modality with self-attention, and once we get to the embedding pooling layer, we fuse the representations corresponding to the special tokens CLS for text and VID for video, either by concatenation or dot product. Next slide, please. So in between the two is mid-fusion, using techniques like co-attention. Co-attention is a concept that was introduced a few years ago in this paper called Wilbert, and the attention layer here is modified so that the keys and values are from the alternate modality. For example, looking at the text modality, the query will be the text representation, and the key and value tokens are from video frames. The rest of the attention block, including layer norm, feedforward, and residuals, all stay the same. Note that the cross-attention layer can be placed at different levels of the stack, such as after a few attention layers, after a few self-attention layers, as shown here, and this turns out to be important, as we discuss in our results. Next slide, please. Now, we look at some of the baselines that we set up. The first one is a sanity check fixed prediction baseline, where you simply predict the mean of the training label. The next one is more interesting, and it's called the pool baseline. The idea here is to help understand if transformers add any value to begin with. In this model, we average pool the sequence of text and video token embeddings to get a fixed vector for each modality. Concatenate the two and use a simple feedforward network to get the multimodal ad embedding. The next two are transformer models that use a single modality, with the goal of running ablation studies to understand the impact of each of these modalities on the final task. Next, I'll hand over to Myra to talk about our experiments and results.
Thank you, Bharat. Here is our experimental setup. We configure our models to have roughly the same number of parameters. The final embedding dimension is fixed at 1024. In the models that use attention, we use 8 attention heads with a 2048 dimensional hidden layer. We train with a mean square error loss on the quality score prediction task. The labels are normalized from 0 to 100 scale to 0 to 1. We use the Adam optimizer with a batch size of 512 and a constant learning rate set to 10 to the negative 5 for 20 epochs. We report MSE on our 20% holdout set. First, we compare transformers with simple approaches such as fixed prediction baseline and pooling and feed-forward network. we see a 44.67% reduction in MSE over the fixed prediction baseline and 3.25% reduction in MSE over the pooled baseline. This significant reduction indicates that transformers are effective at condensing multimodal sequential input data. Here, we look at various fusion techniques, early, mid, and late fusions. The mid fusion with co-attention works better than other fusion techniques. The result shows that it is beneficial to add co-attention after a few layers of unimodal self-attention. We saw significant improvement from the mid-fusion over early fusion compared to late fusion. It indicates that fine-tuning of the unimodal representations with self-attention is important prior to co-training across modalities for our task. Next, we look at the importance of multimodality. Compared to transformer with text only, we saw 18.94% reduction in MSE. Over the transformer with video only, we saw 1.8% reduction in MSE. This result shows that video is the main driver of quality in our data. Next, we look at the attention weights leading to these special tokens in the co-attention layers. And we find that high weights are placed on the tokens that contain bad quality content in the other modality. Here are the attention rollout maps on the special tokens, VID, and CLS of a low-quality ad from our best-performing model, which is mid-fusion co-attention. We see that the special token CLS places high weight on the visual frame F4, which in this case is a frame with undesirable image. Likely, the VID token places a high weight on token 3 that contains the undesirable word. We also experimented with concatenation versus dot product of the special token embeddings into the regression task. The concatenation of the special token embedding showed improvement of MSE by 1.15% compared to the dot product of the special token embeddings. Our quality observations are following. Late fusion works well for short text sequences, but it tends to amplify noise in each modality. Early fusion combines modalities at the beginning, so we choose to focus on the modality that matters. Therefore, it will be promising to have weighted combinations of modalities with attention. In conclusion, we have shown that transformer models are effective at learning multimodal representation for detecting bad video ads. We think that we can extend the work to include more modalities, such as audio signals or in-video text. Other interesting extensions include multitask learning with tasks such as click-through rate prediction or using additional contrastive learning objectives from user co-clicks. Thank you for watching our talk.